Okay, let's look at the homework 18, problem number 5, right? So we want to evaluate this double integral over the part of the surface z equals 4 minus x squared minus y squared that is above the xy plane for vector field is x comma y comma 0, right? So let's draw a picture, right? The surface is going to look like this. So it's going to be, let's see, here's the y-axis, and here's the x-axis, right? And the z-axis is up here, right? All right, so it's a paraboloid, so it's going to look kind of like this. So on the bottom, so let's say on the xy plane, so that means that the z equals 0. So that will give you x squared plus y squared equals 4. So it's just a circle with radius 2. So it's going to look like this. So the intersection of the surface with the xy plane is going to look like this, right? So that's 2 here and 2 here, and -2 there, and -2 there, right? Then it's a paraboloid, so it's going to look kind of like this, right? Then let's see, so that's going to be right here is 4. So that's the top of the paraboloid. All right. So the surface we're looking at is going to be, so we're talking about the surface here. So it's the part of the surface. So we are looking at this surface here. And of course the back side too. So maybe I'll just do that. So this is the surface, right? Without the bottom, right? But without the bottom, we cannot do the divergence theorem. So we're gonna try to add the bottom too. But the bottom side, so right here. So if you look at the bottom, what would be the normal vector, right? Outer normal vector on the bottom would be, of course, it's a pointing straight downwards. So that would be -k vector, right? Then luckily, if you compute, you know, f dot with -k vector, right? Since there's no z component is 0, so this is going to be actually 0, right? So there's no contribution from this. So we can add this bottom piece onto here. Then we do divergence theorem, right? So I'm gonna call this bottom piece, say disk D or something like that. Then we know that the disk D has no contribution. So if you look at a double integral over sigma f dot n d sigma plus the bottom piece, which is over the disk, and f dot n d sigma, right? So we know that this guy has no contribution because this is going to be 0. So we just found out. So this is going to be 0, right? But from here, we can apply the divergence theorem. So instead of the double integral over the surface of this solid, we can do a triple integral, right, over this solid. So I'm going to call this solid, let's say S or something. So solid S, right? So this entire solid, I'm going to call it S, right? Then we can just take the divergence of F, then d tau. So that's just the volume element, right? But if you take the partial of, sorry, not the partial, the divergence of f, it's going to be simply, so triple integral over the solid S. Right, partial with respect to x is 1. plus partial with respect to y would be 1, right? And partial 0 with respect to z would be 0. So you just have that d tau. So that's just going to be 2, right? So that's going to be 2 times the volume of the solid S, right? Now we have to find the volume, right? So this is going to be a double integral, right? So the volume, I'm going to call it, so V is going to be, so it's we're going to integrate it, right? And over this disk, so since it's a disk, I'm going to use a polar coordinate. So the volume element would be r dr d theta, right? Then the surface equation is 4 minus x squared minus y squared, right? So we know that the x squared plus y squared is going to be r squared. So this is same thing as 4 minus r squared, right? So we're going to have to evaluate double integral 4 minus r squared times r dr, and r is going to go from 0 to 2, right? Then after that you have to cover the whole thing, so the theta is going to go from 0 to 2 pi, right? So this is going to be so it's going to be 4r, antiderivative would be 2r squared, and you have minus r cubed, so antiderivative would be r to the 4th over 4, right? Then we just have to go from 0 to 2, right? Then we still need to integrate from 0 to 2 pi, and with respect to theta, right? So this is going to be, I plug in 2, so that's going to be 8, minus plug in 2, so that's going to be 2, and then 2 cancel out 4, right? And plug in 0 is 0, so this is 4. Then integrate that from 0 to 2 pi d theta, right? So this is going to be, let's say that's 4, integrated 4 theta, and so it's going to be 4 theta, and going from 0 to pi. So plug in 2 pi, so it's going to be 8 pi minus 0, so that's 8 pi. So this is 2 times 8 pi, which gives you 16 pi. All right, so that's that, right? But to apply, make sure to know that in order to apply the divergence theorem, we have to have the entire surface boundary, including the bottom, because the solid has the top curved surface and also the bottom piece, so we have to consider that. But in this case, luckily, and the bottom piece has no contribution, so it didn't really make any difference. Right? That's it. I hope that this was clear.